Okay, so today we're going to be speaking about 3D printing and additive manufacturing, and specifically taking a deep dive into some of the technologies, the ROI, and all the indications that you can really do with 3D printing. So Richard already gave me a pretty great introduction, so thank you, Richard. Again, my name is Minh. I'm a dental technician originally from Canada. Now I'm based in Southern California. In my spare time, I run a blog called Dental Tech Tips, where we focus on the latest and greatest in dental technology. So if you want to find me online or via social media, that's where you can find me. So some prerequisite knowledge. If you are brand new to 3D printing, you have no idea about 3D printing at all, there's this little QR code up here. I'm not sure if it's up on the Argen YouTube channel just yet, but we did a webinar last week where we kind of did a very basic primer, an introduction to 3D printing. So the basics of 3D printing, and just to kind of get you up to speed to some of the very fundamental concepts behind it. I'm not going to go too deep into the fundamentals. We're going to go a little bit deeper into specifically why I think 3D printing is so exciting, and what you should be looking for when selecting a 3D printer or getting into 3D printing. So yeah, scan that QR code and you can check out the video on the Argen YouTube channel. So of course I also run the group on Facebook. I always plug this. It's the Asiga Dental Experts group. We have about just under 10,000 members now. And it's just a great group, and I always try to plug social media because very much like being at Chicago, being online is like going to one of these conventions pretty much every day, right? And you get to share, collaborate, see all these cool, new, exciting things that some of our peers and colleagues are doing. So it's just been a great way to connect and really advance and learn and kind of leap forward on the shoulders of other people's work. So it's a great way. I always plug people to at least go on Facebook. If you don't have an account, create one just for dental, just to get into some of these groups, just because it's a great resource for you to learn. So some factors to consider when looking into getting into 3D printing. And when you look at 3D printing, there's a number of different technologies, a number of different price points. This one here, I did a webinar last year actually with Evident, and we did it basically where we compared 3 different printers at 3 different price points, just to kind of compare, what kind of value proposition are you getting between the 3. So if you want to, you can scan this one here, and you can follow that and watch it on YouTube. It was a fun talk, very casual, very nice and neat, and I had a great time with them. So when you look at 3D printers here, you're going to see there's multiple different price points, multiple different resin philosophies, ease of use, accuracy, all these different things that you want to consider, right? And these are probably some of the most popular printers here. But what you'll see is most of these nowadays they have open resin as their philosophy, right? Some of them are closed. I will speak a little bit more about why I think open is so important. But these are some of the factors you want to consider, and we'll kind of dive into each one of these metrics a little bit. Compared to a few years ago, you'll see the technologies have changed quite a bit. Everything's kind of converged back to towards DLP, which is kind of the de facto standard. Again, I'm not going to get too much into detail regarding the actual technology, but the simplicity of it is something like a Formlabs that we had here with the SLA is like a single laser that's drawing something out, right? Which is a little bit slower, like drawing something with a pencil. Whereas DLP is like if you had a stamp and you're stamping each individual layer. The downside of that, of course, is when you're printing with a DLP printer, to keep the resolution very high and also keep everything very accurate, they keep those build platforms a little bit smaller. So you're going to see all these build platforms depending on their size, right? So when you go up to some of these more premium printers that have larger build platforms, they have to up the resolution, they have to decrease the pixel size. So you really have to be careful when looking at these numbers to make sure that you understand what you're actually looking into. So specifically, my brand of choice is Asiga. I've done a lot of testing with a lot of printers, and we landed on Asiga as a brand just because I found it met all of the metrics. And when we go back to that, comparing 3 different printers at 3 different price points, yes, the basics of every single printer is there's some kind of build platform, there's some kind of resin vat, and some kind of light curing engine. That's the basics of 3D printing. So what are you getting at different price points, right? Why is this better than that? Why am I paying more for this? Why is it worth it, right? So with 3D printing, there's a lot of dynamics to it, right? If you're used to milling, if you're used to working with a lot of static objects, for example, like a zirconia disc from Argen, you're milling a static object. You're removing material from the disk, everything's being reductively done, but the material doesn't move. When you're printing, though, you have fluids, and these fluids end up flowing, and they're being pulled apart, they're viscous, they're thick. So when you're pressing this in there, and then you move that build platform out, that creates a void. And when you have this void, what happens is you need to wait for it to fill back in. So the first thing that I'm going to talk about is this smart positioning technology that Asiga has. And they have a whole bunch of technologies that they call their process monitoring technologies. And why this is important is because SPS, what it does is it puts 4 little position encoders underneath the actual build platform. And what this does is it senses the amount of pressure exerted on the glass. So why is this important? So again, like my example where you have all that resin that needs to flow back into that void that's left behind, a lot of printers, what they do is they use what's called a predetermined wait time. So you press the build platform in, you lift it up, it waits 2 seconds, or roughly how long it takes for it to think that that resin's going to flow back in. What this does instead is the SPS system waits and senses for pressure. So once all these 4 sensors are green, that's when the light exposes. So rather than waiting for a predetermined amount of time, what it's doing is it's sensing based on the dynamic pressure of what's actually happening here. So it ensures that there's enough material underneath the build platform to cure, and that it cures quicker. And the reason it cures quicker is when you have large volumes of build, let's say at the beginning you have a lot of bases and just a lot of models, and as you continue to build up and up and up, you're going to have less build areas, right? You're going to have cusps, you're going to have little tiny features. So as you get to the end of the build, the SPS system is going to engage much quicker, and you're going to be able to cure things much faster. So versus a printer that doesn't have this technology, it's going to have to wait 2 seconds, even at the end, even though it doesn't need to wait that long for the resin to flow back, where this is a little bit more dynamic. So it's available both in their Pro 4K and their Asiga Max. So this technology is across all of their printers, and it's very reliable, and you can turn it on and off dynamically as well when inside their software. The next thing that they have inside of their printer specifically is the internal radiometer. So what Asiga does is they calibrate all of their light engines at the factory, and they pair it with an internal radiometer. So underneath the printer, you have a projector that projects a whole bunch of light, and then right above that, they have an internal radiometer. And what that does is it ensures that the projector, because these light engines over the life of the printer will eventually emit slightly less light, right? And you want it to emit 45 milliwatts per square centimeter throughout the entire life. A lot of other printers don't have this, right? So if they're LEDs, they're going to output a certain amount, or they're going to give you 2 LED panels because at some point you're going to have to swap them out. But what this ensures is when it senses that it's dropped by 2%, it's going to bump up the power being delivered to that projector by 2% to account for that loss over the age of the printer. So you're always going to have a consistent amount of cure and light to your build for the light for the printer. So this is very important, number one, for making sure that you're getting the proper amount of cure every single time. So you hear it very often, 385, 365, 405, and some of these printers have dual cure light engines. So what does that mean, right? And why is 385 specifically very important? So what we're talking about with those numbers is wavelength, right? So a longer wavelength is actually just a bigger space between each one of these dips and rises here, where a shorter wavelength is much shorter, and it packs a lot more energy in the same amount of space, right? So 385 is a shorter wavelength compared to a 405 nanometer wavelength. Not by much, but enough to make a significant difference in photo initiators. So why is that important, and why can't we just use any kind of light to cure things? Well, when you look at, let's say, even this laser here, right, it's outputting primarily 670 nanometers in terms of wavelength. But it's not a perfect light source. The dead center of this laser probably is 670, but it can be anywhere from 630 all the way up to 700. So very much like this diagram here, so a 385 nanometer light source will primarily output 385, but it outputs all this other light too that falls off anywhere from 370 all the way up to 410, because light sources don't emit perfect light. And very much like that, there's overlap. So a 405 nanometer wavelength will output anywhere primarily from 405, but it will also cover that 385 range and all the way up to 435. So what does that mean? So if you see a lot of what these printer companies say in their marketing is that, oh yes, we have a dual cure engine because it covers 405, but it also covers 385. The problem with that is it covers 385 at about 10 times less power. So what you'll find is if you end up getting a 385 nanometer resin and you put it inside your 405 nanometer printer, it's going to cure just fine, but it's going to take 10 times as long for that build. Whereas a 385 is going to cure optimally at the right speed. And you can also cure 405 nanometer resins 10 times slower with a 385 nanometer light source. So why does this matter? Well, if you look at the actual photo initiator, so what's inside of a print resin, you have monomers, oligomers, polymers, and photo initiators, and all these additives and stabilizers. But the most important thing I would say is the photo initiator, and it's a molecule that essentially is sensitive to light. So when the light hits this molecule, it kicks off that reaction, and that's what causes everything to polymerize. So what they found in studies is that 385 nanometer photo initiators, there's just more of them, they're more reactive, and they're more effective. The other thing is, of course, you'll find that 405 nanometer light engines are cheaper, easier to source, and more readily available, whereas 385 is slightly more expensive. But you're going to get much, much better results, and you're going to have much better resin availability across a whole range of indications, whereas 405 is a little bit more limited, and it isn't able to cure all the different resin profiles as optimally. So next up is pixels and accuracy. Of course, we're in America, and as a Canadian, I'm fascinated with the culture of guns, so I'm going to use target shooting as an analogy. So something can be precise, but not accurate, right? So this one's right here, it's precise. They're hitting everything within a certain range, all the points are very, very close, right? But it doesn't have accuracy. It's not hitting the intended target, but they're repeating it over and over again very well. This one's not accurate, not precise at all. It's all over the place. This one's very accurate, but not quite as precise. You're within the target, but it's kind of all over the place. It's not repeating with enough consistency. Whereas you can be very accurate and very precise. And this is kind of the goal that we want in dentistry, right? And the ultimate goal of how we measure accuracy and precision is how close this is to the source data, so to an intraoral scan and ultimately to what fits in the mouth. So what I've found is in our tests, with the Asiga, it kind of hit all the marks for us in terms of accuracy and precision, right? Because you want that repeatability, but you also want that accuracy to your source data. And then, of course, precise material curing. They have over 500 validated resins, and I'm very big on open materials just because, let's say, for example, you get into a printer ecosystem, but it's closed, right? So this is where the printer manufacturer has their printer, but they only allow you to print what materials they've validated or is within their ecosystem. But let's say, for example, Argen comes up with a fantastic splint resin that just completely revolutionizes everything, right? But you're locked into that printer's ecosystem. You've lost all your competitive edge. You've spent all this capital expenditure, but you're not able to use the latest and greatest. The nice thing about Asiga is they've taken this open philosophy and they've partnered with a number of resin companies in dental, but not just in industry, in multiple industries. And it's been really great because, number one, their printers are excellent, and they validate them with, whenever somebody has a resin that they're trying to validate, they typically go with Asiga because of the granularity of control, that repeatability, the accuracy that they're able to get with their resin profiles. But again, with that open philosophy, you're not locked in, right? If I find that there's a better material, I'm going to go with that. I want to have that option to be able to offer to my clinicians. So an open philosophy is very important when selecting a printer. I'm not saying Asiga is the only one that has this, but you want to make sure that whoever you are selecting, they give you that option, right? You don't want to have the manufacturers dictating to you what you can offer to your clients. So we're going to look at a little bit of the ROI, right? So the ROI of 3D printing, I mean, obviously it's not cheap to get into these things. So we want to make sure that whatever our investment is it makes sense for us. So how do we calculate ROI, right? ROI is pretty, the formula is actually pretty simple. How much you spend up front, how much you could potentially make, and over a certain amount of time. So this is the formula there. But there's other factors to consider when looking at ROI, right? It's not just the capital costs that you're putting into it. There's the time that you're putting into these things. There's the effort. There's the excess cost of shipping, duties, taxes, depending on where you're located. All of these things matter, right? So you have to look at what the stress, how much of a learning curve is there to get into this system, because time is ultimately more important than money, in my opinion. Maintenance, downtime, getting your team on board with these things, right? Because you may be the one making the purchase decision, but ultimately your team has to be able to be the one that is going to be choosing and working with this, right? So if it just sits in the corner and collects dust, it's not making you any ROI. Also looking at the replacement parts, warranty, availability, and the ability to service all of this is very, very important. And of course, you got to look at some of the prerequisite costs, right? It's not just like you buy a 3D printer and that's it. You have other costs that come ahead of that. In order to get digital impressions in, you need portal software, you need CAD software to build models. You need all of this ahead of time, right? So a lot of us already have this. If we're digital, maybe you're outsourcing your models now. So these costs may have already be paid for, right? But if you're brand new and you just want to get the digital, then this is something you have to consider as well. Again, upfront capital costs on these things, you have other things as well. Post-processing units. It's not just a printer. You have to look at the curing unit, the washing unit, training, installation costs, anything that may be associated with that. You also have to look at the cost of ownership and running this over the life of the printer, right? So how long does it take somebody to calibrate this thing? How many times do you have to calibrate this thing? What happens if you have downtime? What about replacement parts, warranty, all this? Other ongoing costs are the materials, the disposable materials that come with this as well. So things like nitrogen to create an inert environment specifically, solvents like isopropyl alcohol, and PPE and all that stuff also matters, right? Because ultimately you're working with these resins, you want to make sure that you're keeping everyone protected and safe. So all of these are factors to consider when looking into 3D printing. So it's a little bit overwhelming, again, because there's all these different printers, all these different technologies, all these different price points, and how do you get a more apples to apples comparison when looking at something, right? So very much like real estate, when you look at a house and you're trying to compare one house to another in a specific area, you look at the price per square foot, right? And that gives you a pretty good indicator of how much value you're getting when purchasing a home. So very much like that, you look at these printers and you look at what the cost of the printer is per square millimeter of build platform, right? So then what you do is you look at that and you go, okay, well, this is how much it costs per square millimeter of build platform. And that gives you not the only indicator that you should be using, but it gives you a better idea of, okay, well, am I getting a good value for this? And then you can look at all the other technologies, right? Is it open? Is it, how fast is it, right? So you can look at this next slide here. So you got to look at the speed and the accuracy, what layer thickness you're able to do, what materials it's able to do, and how fast it is and how accurate it is to the original source data. So we did some studies on this, and the Asiga 4K actually came up, the most accurate and actually the fastest with some technology that I'll tell you about in a little bit. So the other thing that let's say you're looking into 3D printing, maybe you're outsourcing right now, does it make sense, right? So one thing I always say is always try and outsource when you're first getting your foot in the door, just because it makes a lot of sense. It's an easy way to get up to speed. And then after a certain amount of time, if you look at what your outsourcing bill is with a specific company, if your monthly bill makes enough sense for you to bring it in-house, that's when you should look at it, right? You shouldn't get into 3D printing if you don't have the capacity for it. But it's something to really consider and make sure that you're making an educated decision. So let's go over some of the indications of what you can 3D print. You can pretty much cover every indication in dental nowadays with 3D printing. The limitations on the materials, there's still quite a bit of a way to go with 3D printing, but I think it's a very exciting time because it's still very early on. So the earlier you get educated with these things, the earlier you can learn and make mistakes, the better it's going to be once these materials and technologies become more mature. So with 3D models, and this is pretty much what everybody kind of gets into 3D printing with, kind of reluctantly, I'd say, is because as technicians, we are very hands-on, we're very tactile, right? And if you want digital impressions, which all of your clinicians are purchasing, and you want your technicians to work, especially the more old school ones, they are going to be kind of hard to switch to a model-less kind of philosophy, right? So you want to still provide a model that they're able to check things, check occlusion, check contacts, so they feel good about it. So I always call them fancy restoration holders, really, because my philosophy is we should be trusting the CAD. But if you're going to go this route and you're going to have technicians that are going to be grinding on things, right? You want those contacts, you want everything to be as accurate as possible. So reluctantly, a lot of us are going to have to do models, and these models are almost always a negative ROI because it's not something you make money off of, it's something that ultimately goes in the garbage. So there are some indications that you are able to make some money off of, right? So diagnostic models, I find, are very exciting because, number one, digital diagnostics are much, much quicker when done digitally. But also you can charge for them, right? Where before you would spend 2 hours doing a digital or a hand wax up, and what can you charge for that? $20 a unit? And you're wasting your whole day where you could have built up, a full mouth crown, full mouth crowns. Study models as well. So if you have some doctors who are doing ortho or anything like that, you can print study models kind of on your off time. And that's a very easy way to make a little bit of money and have the printer pay for itself during off times. So there's all these different kind of models. You can do crown and bridge models, right? Why do we want to do it? We want to check for margins, verify fit, check contacts, make sure everybody feels good that what they're getting and sending out looks good. Removables. The nice thing about removables is when you're doing these things traditionally, what you'll find is you have either alginate impressions that are poured at the office. Maybe it's some assistant that doesn't necessarily know how to pour models very well. It has bubbles. Maybe it's just not a very good model. The expansion rate is a little bit different. With digital, it doesn't care, right? You get a digital impression in if it's whether it's for a partial, whether it's for an implant case. The accuracy is going to be the same. And when you print these models out, it's going to be the same. So we noticed quite a bit more accuracy and better fits, and the feedback was really great with removable specifically because you're actually getting more accuracy and better results when compared to alginates or cheaper stones. Diagnostic models, we covered that a little bit already, but again, you can print these off. And the nice thing really is, let's say you have a patient that's not really decisive, right? They show them one of those LVI kind of charts that have triangular, square, ovoid, all these different styles. If I have 5, 6 different libraries, I can design all of them and switch the libraries relatively quickly. I'm not going to say instantly, but I can switch all of those pretty quickly, and then I can print off 5 different diagnostics in the same amount of time, right? Where if you're hand waxing 5 different diagnostics, no way, I'm not wasting my time doing that. So it augments your ability to give a little bit more, many more options to your clinicians. Implant models, very much like crown and bridge, but you want, again, if you're working with a digital implant analog, you want a model that's able to fit and snap in there really good, right? And you're also going to have to print a gingival mass material. A little piece of advice here, if you're not familiar with it, what I actually do is I just print it in the model, regular model material rather than the gingival mass material because I find that they're very brittle and hard and they're not quite the same as the silicone. So what I do is I'll print it in the model material, and duplicate it, make an inverse, and then fill it with your regular gingival mass material, and then you can check it, right? But very often we just print it in the model material, and we don't even need to check it because our designs, again, our emergences are designed in CAD. So it's just a way to verify. But if you like to have that feedback, then just print it in model material, throw it in the same job, and then you can duplicate it in your regular gingival mass material. Ortho record models, again, you can get some white resin and just print those vertical for any doctors that may want ortho study models. And then clear aligner models are very popular as well, right? I'm not a big fan of doing clear aligners if you don't have kind of the automation behind it because trimming the actual aligners is not very fun. But it is an indication that you can do, and again, it's a great way to kind of augment your production if you want to offer clear aligners. Then you can bring it in-house, print off all these models, and make a bunch of thermoform suck downs, and it's a great way to deliver an extra product. So orthodontics specifically, so again, ortho models, there's ortho model resins that you can do ortho on. You're gonna want to have like kind of a spray separator that's silicone based. if you're going to be working with ortho, because they will bond to the actual models. Again, clear aligner models. You can also do indirect bonding trays. You got to make sure, number one, your state regulations, whatever local regulations as well, allows for you to do indirect bonding trays. But it's very kind of interesting, because very often what orthodontists are doing is they're placing these brackets manually. With an indirect bonding tray, you do all this in software, everything's already planned, have all these brackets placed inside of that tray, and they put it all in at once, right? So it saves the orthodontist quite a bit of time. But again, you want to make sure you're checking your local regulations, that you're able to work with them, or maybe they do the planning and you simply just produce these for them. And then, of course, we look at direct print applications. So rather than making models that you make suck down thermoforms on, clear aligners, they have clear aligner resins that are in the works. The big problem with them is they're kind of brittle and they're not very, very robust. Again, these are only meant to be in the mouth for 2 weeks, roughly. But again, clear aligners, direct print applications are very exciting. I don't really have an a cost per print for those, because the pricing is a little bit kind of ambiguous. But yeah, this is kind of some of the stuff that's in development in terms of directly printing for ortho. 3D printed appliances are probably the easiest way to get into a direct print application. And when I say direct print application, that means something that you're printing that's not a wasteful item like a model, but something you're printing for a profit, right? So splints, night guards, super easy way to get into that. If you don't know how to design them, then the 3Shape has an automated workflow for that, where you can just drop it in there and they'll design you an automated night guard. But it's nice, because if you're doing these things traditionally, they have a lot of thermosensitive resins that act very much like the traditional counterparts, but they're done much more efficiently, much more time efficient, and with much less waste. And I found that the economics of doing splints and night guards digitally at a certain volume, once you get to that point, is often cheaper than doing it traditionally. And also you can do snoring, sleep apnea devices with those resins as well. So another very popular one, of course, is surgical guides, something like a very simple single unit surgical guide that you put a sleeve in there. Maybe your doctors want to do the planning themselves. If you're not familiar with it, that's fine, but you can offer it to them and say, hey, you know what, if you're making your surgical guides now and you're getting it produced by a manufacturer, I'd be happy to print them for you, right? So again, making your printer work for you during its off time to kind of pay itself off, right? Perio guides, same thing. So if you're designing all these things, so we do a lot of interdisciplinary cases where very often, you need to do crown lengthening or something like that. So inside of software, what we can do is we can design these perio guides with little windows inside, and you can print these off, send it off to the periodontist, and they can just do some crown lengthening based off of your diagnostic. So it's a very predictable way to get good crown lengthening. Prep guides, very much the same thing. If you guys see them online, sometimes it's like you're printing these things with a bunch of fingers. And what you're doing essentially is you're printing a shell that's representative of your final prosthetic, what you want. And then the dentist can use this when prepping. They can see how much clearance they have incisally, labially, and interproximally. So this is another great way you can deliver this. It gives you, number one, better results, because their preps are going to be much closer to what you actually need in terms of space. But also you can charge them a little bit for it, right? So that's a great way to kind of bump up the lab bill a little bit. And verification jigs. The downside of this is if you're doing verification jigs, you want to make sure that you're sectioning these things or cementing them onto a model, and so that you get passivity according to that model, right? So you're not verifying off of a digital impression and letting your doctor know to really, really verify with that everything is fully seated, and then segmenting them and luting it with composite, because a lot of these resins are composite based, so they'll bond just fine to the composite and just make sure everything is splinted together. But verification jigs with a couple of tie bases inside give you a great way to do verifications for implant cases. So provisionals, we do a lot of try-ins. So if you're doing a diagnostic for a full pros case and you need to open up the video, right? You can print off some temp shells that are like tabletops that sit over top of everything. And that gives you, then they can just try it in, check the vertical, check the aesthetics, mark things up as needed, take photos, and give you some great records. So you can do that very quickly, and it's much nicer than those composite mock-ups that they filled the matrix material with and they place it in there. So try-ins are a great way to use temporary materials. Provisionals, obviously, little tiny temporaries. If they want marginated temps, and then they can send you a scan. We do those occasionally, but that's kind of more for chairside, right? So if you work chairside or you're in an office, printed provisionals are great because you can design them pretty quickly off CAD software by mirroring what's already there existing, and then it's printing for you while you're doing other things or attending to other patients rather than manually trying to adapt a temporary. Custom trays as well. That's another easy way to get into 3D printing and again, making some kind of ROI. Rather than making these things traditionally, especially if you get a digital impression in, you want to make a custom tray digitally so you get it as quick as possible to get a border molded impression. But how many of us get border molded impressions anyways, right? So RPD frames, this is kind of neat because it's not, print resins aren't very versatile for RPD frames. There's not many resins, like especially flexible ones. But what I do here is I'll print it off in a try-in material, and then we will send it to the doctor, right? So rather than either having a wax up and showing it to them, they can actually try that in the mouth. And if they like the design, everything is good, then we can proceed to take that design and send it off to SLM, and they can either laser melt it for us, or we can bring it back into the lab, burn out that pattern, and cast it, right, if you're casting your own frames. Copings, bridge frameworks, all these different castables. Of course, I find it's really nice because when you're milling wax, you always have these burr compensations and the margins need to be a little bit thicker. Whereas if you're printing these things, the accuracy is actually a little bit better and the fidelity of the margins, and there's no burr compensation. So if you're doing things like pressables for veneers, crowns, one thing I recommend actually is, again, using a Asiga dental model. You can burn it out at 915 degrees Celsius for 1 hour, and that'll work just fine. And the reason I recommend this is rather than running two jobs, right, so where you're printing models and then you have to switch everything out and then switch it into castable resin, you can actually just throw it into the dental model build at the same time, and it'll allow you to take those, invest them, and then burn them out. And you get pretty good results. The casting resins will give you more fine results. Asiga Supercast is really, really good for that. But I mean, if you're doing something that has pretty sufficient thickness, this works just fine as well. 3D printed dentures. So digital dentures is kind of the hot topic, right? Everyone's really excited about digital dentures. The materials are getting there. There are some really good validated resins. The aesthetics for me are not quite there. I mean, aesthetics is kind of very important, especially for patients, right? So digital dentures, what we use them for specifically is monoblock try-ins. So what you do is you get a digital impression in, you design it all up, you print it in a try-in material, and you send it to the clinician, right? So this way, it's a quick way to do it, number one. But number two, if they need you to make any changes, you're not ripping apart your whole setup by hand and spending another 45 minutes to an hour to reset it. If they go, okay, well, we need to move the midline 1 millimeter to the left, you go into your software, open it up, it takes you about 10 minutes to move everything that way, and then print off another try-in, or if they're just happy with that, go ahead and take it to final. If they make little markings, okay, well, we want the buccal corridor widened, or we want certain changes, we wanted a completely different library, that makes things a lot easier. And there's some workflows, I speak for 3Shape about it, but where you can scan your monoblock try-in, let's say there's a wash impression on it, right? You're able to bring that back into your software, adapt that wash impression to the original setup, and then just print off a new try-in or take it to final depending on what your doctor wants to do. Again, partial dentures, that same try-in philosophy, right? So if you're doing all that and you can go ahead and print off a partial try-in in a try-in material as well. So calibration, I spoke about this very briefly, but calibration is very important because this is how you make sure that your printer is accurate and precise, right? So why is it important? When should we do it? Why should we do it? So with Asiga specifically, they recommend that you check your calibration every 20 to 30 builds. So that doesn't mean that you have to do a calibration. So the nice thing is, where I am in California, the weather is really, really nice and stable all year round, right? The printer doesn't really move. There's not much temperature change. There's not much that happens to the printer. So it's not going to fall out of calibration very often. But you should still check it to make sure that it's accurate. The other thing about calibration is you want to make sure that it's something that's quick, simple, and efficient. So some of these printers, when you're calibrating them, they have these glass plates that you got to put in place. You have 4 or 5 different bolts and then 4 or 5 different Allen keys that you got to put in. You have to have a sheet of paper underneath and calibrate it. With Asiga specifically, they have a single point calibration system where essentially you loosen up that bolt, drop the platform to the glass, have it pressed fully against the glass, and tighten it and set 0. So it takes 2 minutes to do your calibration. Whereas I've done some calibrations on other printers that it takes you, 3 tries, 20 minutes each time, you're there for an hour. So the simplicity of a calibration is very important because if it is out of calibration, you probably had a failed job immediately before it. And if that job is failed, it's going to set you back on your production, right? So you want to make sure you're able to calibrate things really, really quickly and really simply, and anyone on your team is able to do it. You don't need to be a rocket scientist to calibrate printers. And then there's printers that are meant to be really user-friendly that don't allow any kind of calibration at all, right? And what they do to kind of overcome that is they kind of press in on their Z depth a little bit more, so they press a little bit harder on the glass, as well as they kind of adjust their burn-in rates to make sure everything adheres to the build platform a little bit better. So you get a little bit less accuracy in the Z-axis on some of those printers that don't have any calibration, right? So I like to, of course, have calibration, but it should be easy and simple to do as well. So I was just speaking about burn-in rates, but let's talk about some of the advanced settings and why I go with Asiga specifically. And the reason for it is you get this granular level of control, right? It's a printer that was built by engineers. They're not in the dental industry initially. There were a bunch of engineers who just happened to stumble into dentistry, and we've kind of adopted this as one of the most popular printers. But when you get to the advanced parameters on your build, you're able to set all these little tiny settings. So again, I was saying, when you're printing, it's a dynamic experience, right? So it's pressing into this viscous liquid. It's pulling out of this viscous liquid. If you have a larger printer, it's going to create a vacuum almost, like when you're trying to pull something out of a viscous liquid. So you can adjust your lift rate, your acceleration rate, deceleration rate, all of these little things to really tweak your print so you get optimal prints. You don't have to. That's the nice thing, because you have all those validated resin profiles. All the manufacturers and Asiga, they've done the hard work for you already, and their profiles are pretty optimized. But sometimes we all live in different climates. We all live in different locations. There's little tiny different variances in everything that we do. So if you need to adjust your burn-in rate, this is typically the only one that you really need to do. If you find your models are either not adhering to the build platform, or they're just falling off a little bit, or they're a little bit too light when you take them off, you can adjust this number in about 10-second increments. 10-second increments just to increase how much time it's cured and how cured it is to the actual build platform, so your prints really stick. But beyond the granularity, I'm a little bit of a nerd, and we like to dive in a little bit deeper, right? So how can we have fun with this? So a lot of the stuff I'm going to show you here now is not really practical, but it's really fun, and it shows you the power of what you're able to do and the level of control that you have with the Asiga printer specifically. So Asiga multi-range, we'll kind of define what a range is in terms of printing, why you would want to do multi-material printing, and then some of the background on these. So it's kind of hard to see, but there's this very faint line here. And this line is super, super, super exciting, because what you're seeing is this is printed in 100 micron layers, 100 microns, because from here to here on most models is low poly, low detail material, right? It doesn't need to be accurate from here up until you reach the margin. And then from the margin up to the top of the prep or to the top of the anatomy, you want that to be as accurate as possible. So what we're doing is we're printing this here in 100 micron layers, and we're switching midway through the print to 50 micron layers. So what that does is it allows the printer, number one, to be faster, but it also gives a lot of variability and flexibility in the materials you're able to stack on top of each other, right? So this is like a clear resin material. This is like a key splint soft, I think. This is a gingival material, temp material. And you can stack all these different materials on top of each other, and that's just having fun. But what is a range, right? So a range is a set of numbers from one point to another, right? That's just what a range is. In terms of printing, what that means is a range is anywhere from 0 to the top of the print, or from this point to this point. This is a range that we define. And you're able to do that inside of the Asiga printer, because it gives you that granular level of control. So multi-range printing was originally intended for the Pro 4K, and I always say it's a little bit of a gimmick because they wanted their printer to be the fastest on paper, right? So how are they going to beat some of these other printers that have non-contact DLP? And essentially non-contact DLP is they have like this oxygen permeable layer that allows the resin to be pulled out much quicker because it's not being peeled from the bottom of the tray. Asiga is using traditional DLP that still needs to peel, but because you're implementing 100 micron layers and 50 micron layers, you're able to get these prints slightly faster. So you can go right on the Asiga website, go to their materials, and there's this configuration file right here, Denta Model Multi-Range, right? And it gives you some settings at the end that you're able to set. So you go in there, you can set, okay, well, I want this range from here to here to be 100, and from here to here to be 50. But you can do other cool things. I want this range from here to here to be printed in pink. I'm going to switch out my resins, and I'm going to print this range from here to here to be in white. So, I mean, is it the best result? No. Am I going to deliver this? Probably not. But again, it's kind of just a proof point, just to kind of have a little bit of fun, right? It's not the best looking result, but it's kind of cool what you're able to do with this. The other thing you can do, of course, is 3D printed splints. So maybe it's a soft material on the inside or on the bottom side here, and then the top side is a harder splint material. So you kind of have like a dual splint that you can do combined together. So how do you do this inside of Asiga Composer? This is kind of give you guys a tour of it as well. So you can design your part, bring it into that multi-range print, nest it inside there, and then you get this, right? So we're going to set that range for the first portion. So we're going to set from the bottom of the print inside the software up to this point. We're going to count what that is. And then we're going to go to the next, to the final portion that we want to print, and we're going to set those ranges inside the advanced parameters. When you nest this in there, you don't want to close the nesting. You're just going to switch the material from one to the other, so it applies that profile to the second one, and you're going to keep your slice thickness, everything the same, and it's going to yell at you and say, okay, well, your ranges are going to be a little bit different, and we're going to have to adjust our ranges here. So from here to here is 7 millimeters roughly, and we can count that inside of the software, and then we can set the second one. The other thing you want to do, if you want to play with this, is you want to create a 0 point or a known point on your build platform, right? So you want to move it either one way or the other, just so when you put it back in there, it's perfectly centered with whatever you're trying to print on the previous build. So for the second portion, again, it's gonna tell you these structures may be unoptimal. Go ahead, hit OK, don't change anything, and then you're just gonna set the second range, right? So from 7.1 up to the top of the print, 13 millimeters, that's gonna be in your second material. The other thing you have to worry about is that the cure profiles on these need to be relatively similar. And the other thing is you want to make sure you're protected, right? So whatever materials you're working with, that they're compliant and you know that they're validated. So make sure you double check those as well. And if you are printing with this, you want to use a low force tray. A low force tray essentially has 2 layers of PTFE in there that allow it to reduce the peeling forces. The other thing is if you're printing multi-materials, you will have some contamination over time. Again, it's a little bit of a novelty, not something that you should be doing regularly or getting the printer specifically for doing this, but it's just kind of a fun way to show you the power of 3D printing multi-materials with this printer. The other thing you can do, again, is it practical? No. Is it kind of fun? Is it cool to show off? Absolutely. So multi-stacking, right? So this is one layer of prints here. We built a whole bunch of rafts, and then we stacked another layer of prints on top, right? And this is built-in functionality inside their software that you're able to do. And you just add a whole bunch of jobs, and you go into the tools, and there's a multi-stack option in there where you can stack a whole bunch of jobs. This is not really practical because, you know, number one, you're nesting quite a bit, taking a little bit of time to nest each individual job, but also these rafts use up a lot of material, right? So it's not practical and economical really, but again, kind of fun, cool things that you can do. If you're in a pinch, absolutely do this, right? So if you got a whole bunch of models, you're over capacity, you know, print 2 layers or print 3 layers overnight as your final job. It's a great way to get your production up to speed a little bit faster. Asiga recently introduced lattice supports. Their original support structures were just straight lines. And if you have these complex structures, sometimes the supports would actually poke through the actual model, right? So when you're printing this, you'd have to cut and grind off all these supports. So with their latest, one of their latest updates, 1.3.4 I think it was, they introduced lattice supports. The other nice thing about that is they introduced undershoots for their lattice supports, right? So very often when you're printing these things, you have this contact point, and when you peel it off, it'll either create like a little divot or a little hole there. So we grind it and you're filling it in. But with an undershoot, what it does is it actually moves the contact point a little bit outside. So the weakest point where it will break, it will be outside. So that way you're able to grind off these little points rather than having a little gouge inside of your print. So that's kind of a neat feature that they've introduced recently. And I'm just going to emphasize the importance of support as well. So a lot of printers, I mean, a lot of these are manufactured overseas. Asiga is a company based out of Australia. They've been around since 2011. But most recently, they set up a new headquarters, a North American headquarters in Detroit, Michigan, right? So there's a lot of great printers out there. But what you find happens is if you don't have the support network, you know, if they're in Europe, if they're in Germany, right, you got to get 5 a.m. to get support from somebody. That's not good. A 3D printer, especially if you have a Pro 4K and you need to ship it back or you need to have a projector shipped out to be replaced, shipping it to Germany is never going to happen, or for them to get you the parts here, right? So their North American headquarters in Detroit, Michigan which is my surrogate hometown. They have all the parts, everything in stock there. But yeah, manufacturer support is absolutely critical, right? Having a home base in North America is very critical to get parts to you in the event that you need it. The other thing that's very important is reseller support, right? You want to make sure that your reseller, whoever they are selling it to you, don't go with the cheapest one. Go with the one that's able to support you after the fact. Are they able to offer you training? Are they able to offer you technical support? If something goes wrong, are they able to pick up the slack, right, with their own manufacturing while your printer's being repaired, right? So all these things are very, very important in terms of choosing somebody that you're going to partner with for the life of this printer. And then finally, online community support. I already plugged the group, but this is kind of one of the factors as well, right? Online community is very important because this is where I really learned a lot of 3D printing from. I learned it from my peers, my colleagues online, right? And we have a group that has almost 10,000 members on there, and they're sharing all this different stuff. That multi-material printing, I didn't sit in my basement and come up with it on my own. I found it because somebody else came up with an idea, and we built on it, right? And we kind of perfected. We figured out what mistakes were. We shared notes with each other. So if you have an issue, you know, you can pop on here, and people are always willing to help. And it's just such a wonderful community. Everyone's so friendly. So I always try to plug them whenever I can. So the last part I always try to cover is post-processing. So when you print these things, they come off the printer, they're not ready. They're probably about 20% cured, right? So you need to finish 80% of the curing outside of the printer. So this is equally, if not more important than the actual printing process itself. So post-processing, you need a way to wash off all that excess resin. So we use these Form Labs form wash units. They're a little bit expensive. They're about $500. But the nice thing is they're a little bit automated. So when they go in there, they wash the unit, and when it's done, it raises itself out so they can start drying. If you're using something like a Joule ultrasonic unit or a shaker, an orbital shaker, those are nice too. They're very economical. You can go online on Amazon. You can buy them for $150 for like a 10-gallon one. But what happens is if you're busy in the lab, you take all these things, you put them in there, and then for 20 minutes you're doing something else, right? That resin is sitting inside of a solvent. And it's also absorbing all that moisture, and it'll cause it to swell just a little bit, right? So with an automated system, what it does is it allows it to be washed for the proper amount of time. And with these, you really don't want to wash them for more than 5 minutes max, but you really want to stick to whatever the IFU is for that specific resin. Because again, they are polymers, and polymers and solvents do not play nicely together. So what they find very often, especially with these new kind of permanent crown resins, is when you toss them inside of a solvent for a very long time, the polymer chains actually start to break down and weaken, right? So you want to wash it for as little as possible, but to get the cleanest result possible. So cleaning, very, very, very important. When you're done, you can dry it off with compressed air, or you can just leave it to dry under a heat lamp or just in regular air. If there's any residual glossy areas, you can get a little spray bottle and just kind of spray it to wash that specific area, get a brush perhaps. And then you can cure it in a validated curing unit. So validated curing units are very, very important. I mean, for resins, they're photosensitive. You can take it, throw it outside, and it will cure to some extent, right? Because under any light, it will cure. But what you want is you want a validated unit, because a validated unit ensures that you're getting the optimal cure. So if you're printing direct print applications that are going into patients' mouths, like a splint, like a night guard, anything like that, you want to make sure that there's no residual monomer, no residual materials that can cause any kind of cytotoxicity, because it's really dangerous, actually. So you want to make sure that you're getting something that is validated. All these, they have a whole bunch of validated curing units. This is probably the most popular one, just because it's, number one, a very, very good unit, but also it has the ability to cure with an inert environment, so something like nitrogen, right? So why do you want to do that? If you've worked with composites before, then you know that you have that oxygen inhibited layer on a lot of these composites. And it's like a little smear layer that you either have to polish off or brush off. But with nitrogen, what happens is it floods that chamber with an inert environment, and it allows that print to print without oxygen, to cure without oxygen, and then it gives you a much better final result that's much more accurate as well, because you don't have to polish off that sticky residual layer. You can also use glycerin, but the trays for the auto flash have these little holes that won't hold the glycerin, so you have to find a slightly different container. But glycerin works as well because it allows all the light through, but it also creates an inert environment. So some of the limitations of 3D printing, I touched on this a little bit earlier, but the resins are really still in their early stages, right? So the materials are getting more and more robust as more development goes on in this space, right? You get permanent crown resins now that have they're ceramic filled, but the materials are not going to be as robust as their milled counterparts for quite a while, in my opinion. And the aesthetics and accuracy still have a lot of room to grow as well. But I think it's a great time to get into 3D printing, because I think if something great comes along, this will all happen very quickly. We all saw what happened with milling. So in terms of some tips and tricks, just to kind of leave you guys with a few tips and tricks. So it's recommended that you mix resins at least 1 hour before. So again, they have all these monomers, oligomers, polymers inside their stabilizers. And these materials will have a tendency to separate depending on how homogeneous it is. So you'll shake these up or keep them mixing, but mix them about an hour before printing, because you're going to introduce air bubbles into the actual resin. So once you pour it into the tray, pop those little bubbles with an instrument, just very much like when you're pouring stone or investment, and then allow it to sit a little bit, so when you're actually printing, you don't have any bubbles inside your print. Keeping your resin vat relatively full as well is very important, right? A lot of people have issues with printing, and they'll print and they go, oh, I don't know, I'm getting a failure. Well, again, because it's a dynamic material, when you press into this, and then it displaces all this resin out, if you have very little resin, it takes much longer, or that resin will not fill back into that void, right? So if you keep your resin fuller, it's going to fill in faster, number one, but number two, it's going to ensure you have enough material to finish your print. The other thing is it applies pressure on the actual membrane itself, making it a little bit firmer, so you get a better print and better adherence to it, so it's not kind of flopping all over the place. The other thing, these are UV covers, right? They block UV light, but they don't block 100% of UV light. So if it's sitting near a window or it's under a direct light, you might have some adverse effects of leaving that print in that build platform in that resin tray for too long. So you want to make sure that if it's sitting in there for an extended period of time, you either cover it up or cover the printer up or move it away from direct light, which will be better for it. Some other things to consider, vertical versus horizontal nesting. So you'll see the prints are kind of nested in all different ways, right? And very much like my analogy of that laser printing versus a stamp, when you're printing vertical, it's more layers. So a vertical print is going to take significantly longer than something that's nested horizontal. The downside of that, of course, is when you're printing something horizontal, you have more forces being exerted on that print. So you're going to get a lot more distortion on horizontal prints. So the most optimal way to print anything is on a 35 to 45 degree angle, just because your cross section of what's actually being printed is much smaller for each individual slice. So you're going to have more accurate prints with a smaller surface area exposed for each individual time. And it gives you a good balance of time versus accuracy. The other thing is, and this is kind of a misnomer, everyone thinks they should print at 50 micron layers for everything. But the studies have actually shown that printing at 100 micron layers for the majority of prints actually makes the material stronger. So the literature shows that 100 micron layer prints are faster and stronger. So unless you need that 50 micron layer accuracy, print at 100 because it'll just double your productivity comparatively, but it'll also actually give you a more robust print overall. And then finally for curing, if you're inserting digital implant analogs or any kind of guide sleeves or anything like that, when you're curing them, just insert them before and then put them in the post-cure unit. That way it doesn't deform, because these things output heat and they output a lot of heat and distortion to these things when they're curing. So you want to put that in there beforehand. So with that, I want to say thank you, and if you guys have any questions, I'm happy to answer. Yeah, thank you.